Assalamualaikum and good day to our lecturer. We are Group 7 and today we are excited to present our mini project, an air quality monitoring system. Our team consists of Izzat Farihin, Haris Hayadi, Muhammad Adam Danish and Ahmedia Mazuki. Next slide. To give you some background, air pollution remains one of the most critical environmental challenges today. So first, air pollution is a major environmental issue that affects human health and the environment. Continuous air quality monitoring helps detect unhealthy conditions. This project develops an IoT-based air quality monitoring system using a CSV dataset, Python, and ThinkSpot. The system monitors air quality index AQI, temperature and humidity, and generate alert when threshold values are exceeded. The project demonstrates the use of IoT and visualization to improve environmental monitoring and public awareness. Now, let's look at the core problem we are addressing. Challenge statement. First, air pollution poses serious risk to human health and the environment. Next, traditional air quality monitoring systems are often expensive and have limited coverage. Third, many areas lack continuous and real-time air quality monitoring. Fourth, delayed detection of poor air quality can increase exposure to harmful pollutants. And last, many existing systems do not provide real-time alerts for immediate action. This is the objective of this project. First, to analyze and process air quality data using Python in Jupyter Notebook. Second, generate alerts when environmental parameters exceed predefined threshold values. Third, visualize air quality data through graph and an interactive dashboard. Fourth, improve public awareness and support better decision making through efficient environmental monitoring.
So this slide will shows the overall workflow of our air quality monitoring system. First of all, the system begins with an air quality dataset that we obtain from Kaggle. The dataset is stored in CSV format and contains environmental parameters such as the date, air quality index, AQI, temperature, and also humidity. Next, a Python program running on Google Colab reads the CSV file using the pandas library. It extracts the required parameters, which are AQI, humidity, and also temperature, and converts each data record into JSON format, making it suitable for transmission. After that, the program sends the data to ThinkSpot cloud using HTTP POST request through the request library. The device access token is used to authenticate the connection and ensure the data is sent to the correct device. To simulate the real IoT sensor, the program transmits one data record every second. Lastly, ThinkSpot Cloud receives and stores the telemetry data. The dashboard is automatically updated with the latest sensor readings. Historical records are saved, trend graphs are generated, and the alarm rules are evaluated. And also, if the AQI exceeds the predefined threshold values, the corresponding alarm is triggered. Overall, this workflow demonstrates how air quality data from a Kaggle dataset is processed, transmitted, and visualized in real time using an IoT platform for environmental monitoring. So now, this slide presents the main features of our ThinkSpot dashboard, which allow users to monitor air quality in real time. So first of all, at the top of the dashboard, there are three monitoring cards that displays the latest AQI level, the humidity, and also the temperature values. These cards are automatically updated whenever new telemetry data is received from the Python program, allowing users to quickly view the current environmental condition. Next, on the upper right side, we have a monitoring history table. This feature stores every data record received by ThinkSpot, including the timestamp, AQI, temperature, and also humidity values. Users can review previous and track environmental conditions over time. At the bottom left, the air monitoring trends graph provides visual representation of the collected data. It plots AQI, humidity, and also the temperature over time, making it easier to identify patterns or sudden changes in air quality. Finally, the alarm panel automatically generates alerts based on predefined AQI threshold. This helps user identify changes in air quality, while the alarm conditions and severity levels will be explained by the next presenter.
Now I will demonstrate our air quality monitoring system using the ThinkSpot dashboard. As the Python program is running, it continuously sends one data every record second to ThinkSpot Cloud. We can see that the dashboard updates automatically as new data is received. First, at the top of the dashboard, we can see the three monitoring card. The first card display the latest air quality index, or we can call it as AQI. The second card is humidity, and the last card is temperature. This value will continue to change as new data is uploaded. Next, on the upper right, we have the air monitoring system table. As the demonstration is running, a new row is added every second. Each row contains the timestamp, AQI, temperature, and humidity, allowing us to view all the data that has been received by the system. Moving to the bottom left, we have the air monitoring trend graph. Here we can observe the changes in the environmental data over time. The blue line represents the AQI, the red line represents the temperature, and the green line represents the humidity. As more data is received, the graph updates continuously, making it easy to observe any fluctuation or trend. Finally, at the bottom right is the alarm panel. During the demonstration, the system automatically checked the AQI value against the predefined condition. If the AQI is between 0 and 50, the air quality is classified as good with low severity. If the AQI between 51 and 100, a warning alarm is generated. When the AQI exceed 100, the system triggers a higher AQI alarm will measure severity. Any trigger alarm will immediately appear in this panel together with its status and timestamp. Overall, this live demonstration shows that our system is able to receive air quality data in real time, update the dashboard automatically, record historical data, visualize trend, and generate alert whenever the predefined AQI conditions are met. And I will pass to the next person.
Okay, so for the future recommendation, the existing project can be easily upgraded into a real world smart city application with few key changes. So the first one is we can swap out the simulated dataset for real hardware, which is we deploying an ESP32 or Node MCU microcontroller with physical sensors like an MQ gas sensor or a Bosch BME680 in the industry to catch live air quality readings on site. Second, switching our communication from HTTP post to a lightweight MQTT protocol will make the data streaming much more efficient, saving bandwidth and battery power for remote devices. And third, we can push alert beyond just dashboard display by setting up things about rule chains. A notification major event could automatically send a text via Twilio or a ping Telegram bot directly. Finally, we can build a simple machine learning models into the Google Colab script would let the system analyze the temperature and humidity trends to forecast dangerous AQI that can be spiked in hours in advance, shifting the project from just reacting to pollution to actively predicting it. So as for the conclusion, this air quality project tick all the right boxes and showed just how practical and powerful cloud-based IoT setups can be for tracking public health. Linking Google Colab with ThingsBots allowed us to build a seamless data pipeline that easily handles, tracks, and charts AQI, temperature, and humidity all on a single live graph. The dual condition AQI alarm worked perfectly, instantly separating safe levels from dangerous ones and pushing out a notification major, the second pollution spike. Ultimately, this project serves as a solid blueprint for modern environmental monitoring, proving that you can leverage accessible cloud tools to build a fast, reliable, and potentially life-saving early warning system. So, that's all from us, the presentation for our project from Group 7. Thank you.